Hi, welcome to Chapter 19, Chemical Thermodynamics, Part 2, where we're going to talk about entropy changes in chemical reactions, Gibbs free energy in temperature, and free energy in the equilibrium constant. So the third law of thermodynamics says that the entropy of a pure crystalline substance at absolute zero is zero. Remember, absolute zero is 0 Kelvin. So if you look down here you have a perfect crystal. All of these are lined up perfectly. At 0 Kelvin, the entropy is 0. So consider all atoms or molecules in a perfect lattice as 0 Kelvin. There will only be one microstate. So if you plug in 1 for W, you're going to get 0 here. Here is a plot of the entropy versus temperature, and you can see during phase changes, the entropy jumps up quite a bit, yet the temperature is staying constant. So standard entropies, these are things you could look up in the appendix in your book, but here is a table of quite a few of them. The reference for entropy is 0 Kelvin, so the values of the elements are not 0 joules per mole at 298 Kelvin, okay? So standard molar enthalpies for gases are normally greater than liquids and solids, but you kind of have to look at the masses of them. Standard entropies increase with molar mass. So the higher your molar mass, the higher your entropy. Standard entropies increase with the number of atoms in a formula. Because you have more atoms in a formula, you can arrange and have more microstates. So if you see down here you have methane, and here's the entropy for methane. Ethane, you now have more atoms, higher entropy, and finally propane. So enthalpy changes, remember this here means change, so enthalpy changes would be delta S. Enthalpy changes for a reaction can be calculated in a similar manner that we calculated delta H many chapters ago, if you remember. What you do is you take the moles of your product times the change in entropy of your product. You sum up all of your products, this means sum, minus the sum of the moles times all of your reactants. Now, when we did this for delta H, a lot of you screwed up this minus. You kind of should put brackets around here because you're going to probably have more than one reactant. You have to sum up all of your reactants, but then subtract them all, where N and M are the coefficients in the balanced equation. So let's do this example for ammonia. So you look at your products. I have 2 moles of NH3. Find NH3 in your table here, and its entropy is 192.5. So you do 2 times that. Minus your reactants. Here are your reactants. So there's 2 of them, right? You have 1 mole of nitrogen. So you find nitrogen here, which is 191.5. So notice the brackets around all of my reactants. I'm going to sum up all of my reactants, but then I end up subtracting them. 3 times the entropy for hydrogen. So when I sum all that up, I get negative 198.3 joules per Kelvin. So the entropy changes in the surroundings. So heat that flows into or out of a system changes the entropy of the surroundings. For isothermal process, remember isothermal means same temperature or constant temperature. Your change in entropy of your surroundings is just equal to Q of the surroundings over T, and Q of the surroundings is just equal to negative Q of the system over T. At a constant pressure, you could substitute out Q of the system with delta H of the system. So then we have this relationship here at constant pressure. Enthalpy change of the universe. The universe is composed of your system and your surroundings. Therefore, the universe is the sum of the system plus the surroundings. And remember, for spontaneous processes, the entropy of the universe is greater than 0. The entropy of the universe can never be less than 0. the entropy of the universe is either staying the same or increasing. So here again, we have our entropy of the universe equals the entropy of the system plus the surroundings. Substitute the entropy of the surroundings with the equation that we found on 2 slides previous. So we have delta H of the system over T. Then we're going to multiply both sides by a negative T. And then we're going to rearrange and basically put this new term in, delta G, which is Gibbs free energy here, and substitute that in where we see a negative T times the delta S. Okay, so here we get Gibbs free energy. Delta G equals delta H minus T delta S, where T here is in Kelvin. So it gives free energy. Again, it's equal to negative T times the delta S of the universe. It is defined as Gibbs free energy, delta G. When the change in the entropy of the universe is positive, delta G is negative. Therefore, when delta G is negative, a process is spontaneous. So for spontaneous, delta G has to be negative. And remember, delta G is equal to delta H minus T delta S. So if we want delta G to be negative, we could look at our delta H and our delta S and figure out what our delta G is going to be. So let's say our delta H is negative and our delta S is positive. So we're exothermic and entropy is increasing. Delta G will always be negative, so we have a spontaneous reaction here. Okay, what about the reverse? Endothermic, and our entropy is decreasing. Well, this will be positive, and this is not non-spontaneous. This is spontaneous. What if they are both negative? Then this is only, so we want it to be negative. If they're both negatives, this term is now a positive. This term has to be smaller than delta H. So low temps. At low temps, delta G will be negative. And what if they are both positive? Positive at high temp, you will get a negative delta G. Why is this important? Well, if delta G is negative, that means your reaction occurs spontaneously. What if we were to plot delta G versus temperature? What would the slope of that line be? Your change in entropy, is your slope. And this is your y-intercept. Actually, let me erase this here a little bit. Your slope would be negative delta S. So it gives free energy. If delta G is negative, the forward reaction is spontaneous. If delta G is 0, you are at equilibrium. Right here, equilibrium. If delta G is positive, the reaction is non-spontaneous. But it would be spontaneous in the reverse direction. That doesn't mean this reaction won't occur. Non-spontaneous does not mean it won't occur. It means you have to apply work to it to get it to occur. So how do we calculate our change in delta G? So the standard free energy changes. So we calculate this similarly to what we did with our delta H and our delta S. You could look up the values of the free energy of formation of your products and your reactants, and then you can sum them up. Again, I'm going to put brackets around here so you remember. You have to sum up all the products, the moles of the products times delta G's of the products, minus the moles of the reactants times the delta G's of the reactants. Okay? So when we have this little naught here, this little 0, that means standard state. And standard state for a solid would be a pure solid, a liquid, a pure liquid, gas. It's at 1 atmosphere, and your concentration is 1 molar. And for an element, the delta G formation is 0 for elements in their standard state. Elements in standard state. So a couple slides ago, we kind of made this table, but here it is again. Here we have our delta H. If it's negative and delta S is positive, our reaction will be spontaneous at all temperatures. An example would be ozone converted to oxygen. If delta H is positive and entropy is negative, it will be non-spontaneous at all temperatures because delta G will always be positive. Say positive. If they are both negative, it could be either or. You got to look at your temperatures. It'll be spontaneous at low temperatures, but non-spontaneous at high. And over here, if they're both positive, again, you got to look at your temperatures. This time it'll be spontaneous at high temperatures, but not at low. So how does delta G change with temperature? Well, it depends on what your delta H and delta S are, right? There are two parts to the free energy equation. There's your enthalpy term, and then there's your entropy term. And really, this term here has the temperature in it, okay? So the temperature dependence of free energy comes from the entropy term, which is this one right here. So since reactions are spontaneous, if delta G is less than 0, the sign of enthalpy and entropy and the magnitude of the temperature will matter to determine if it is spontaneous or not. Remember, you have to get delta G to be less than 0. So what about at equilibrium? Under any condition, standard or non-standard, the free energy change can be found using this relationship here, where delta G is equal to your standard delta G plus RT, the natural log of Q. Remember Q from our equilibrium chapter? It was the reactant quotient. Okay, R here has to be the R that has joules in it, so it's 8.314. Okay, so under standard conditions, the concentrations are 1, so Q would be 1. So natural log of Q would be 0, and this term would drop out. So the change in delta G at standard conditions is equal to the change in delta G at standard conditions. That kind of makes sense. So what happens at equilibrium when Q equals K and delta G equals 0? Remember that plot here? Over here is at equilibrium and delta G equals 0 at equilibrium. So we could plug in these two values into our equation from the previous slide and rearrange, and we get the delta G at standard conditions is equal to negative RT, the natural log of K, where K is your equilibrium constant. And then if you want to rearrange it even further, you could say your equilibrium constant is equal to E raised to the negative standard change of free energy over RT. Again, T has to be in Kelvin, and R has to be 8.314. Now, sometimes a reaction is non-spontaneous, but if you couple it with another reaction that is spontaneous, then the combined two will sometimes result in a favorable reaction. And this is what happens in the biological process of converting ATP to ADP. You have multiple reactions going on, and the free energy from one helps trigger the other reaction to proceed. And that is the end of Chapter 19.